Alright, should be streaming here soon. Just gonna do a quick sound check before we get started. Make sure that we are good to go. I hope that everyone had a wonderful day. Alright, looks like I'm online. Good connection. Alright, cool. Cool. Alright, so hello, brilliant minds. It's MattyAtoms, and today I've got something just a little bit different for you. One of the best parts about running a science and outer space based channel like I have is that I get a lot of people reaching out to me. Sometimes people will ask me what I think about a certain topic, sometimes people will send me different theories and ideas, and that's exactly how I met this man, James Hutchison, the founder of the modest theory. He describes it as a modest approach to the theory of everything. We chatted for over an hour, and I cut it into a 17-minute interview, which I'm about to play in a little bit. But first, I just want to provide some MattyAtoms context. What is a theory of everything? Why do scientists search for it? And what could a theory of everything do for science in the future? So I think it makes the most sense to start with the why. Why are scientists searching for a theory of everything? Well, for starters, quantum physics and the classical model for the universe simply do not get along. Classical physics, the stuff of Newton and Einstein, that your high school teacher swore you'd use at your job, it works beautifully for big things. Planets, stars, galaxies, your car rolling downhill because you forgot the parking brake. The classical model handles all of that with clean, predictable laws. Quantum physics, on the other hand, is the rule book for the tiniest stuff in existence. Particles, atoms, and subatomic particles that behave like they're drunk at a wedding. In the quantum realm, particles blink in and out of existence, teleport, exist in multiple states at once, and change their behavior depending on whether you look at them or not. How vain. But here's the problem. When we try to use the same rules to explain both the giant stuff and the tiny stuff, the math just explodes into nonsense, like actual nonsense. Divide by zero, infinity on top of infinity, your calculator just breaks. Gravity, the big beautiful force that Einstein described, refuses to play nicely with quantum mechanics. It's like setting up Donald Trump and Kamala Harris on a blind date. There's going to be a clash. Classical physics says space-time is smooth and continuous. Quantum physics says everything comes in little discrete chunks. Those two ideas don't mesh, and until they do, we can't have a single unified picture of the universe. And it gets even messier than that. For example, we have never actually found a graviton, the hypothetical quantum particle that should carry gravity in a quantum universe. If quantum mechanics is correct, and it is, it works flawlessly with everything else, then gravity should have a particle, just like how electromagnetism has photons. But the graviton? Still POW-MIA. No sightings, no detections, no tracks, not even a blurry Bigfoot photo. And speaking of missing things, we haven't found the true source of dark matter or dark energy either. The two ingredients that supposedly make up 95% of the entire universe, we can see their effects, we can measure how galaxies appear to rotate too fast, or how the universe's expansion is speeding up, but the actual stuff causing those effects? Nada. Nothing. Invisible, untouchable, completely unknown. And many physicists suspect that these mysteries aren't just separate problems. They may all stem from the same core issue. Our two main theories don't talk to each other. Quantum mechanics describes the small stuff. General relativity describes the big stuff. But dark matter, dark energy, gravity itself, those things operate on scales where both frameworks should overlap. And right now, they appear to clash instead. So think of it this way, right? It's like trying to watch a movie where the left half of the screen is playing Star Wars and the right half of the screen is playing Lord of the Rings. They would be great individually, but completely chaotic together. And this is why a theory of everything matters. Because somewhere in the disconnect between the quantum world and the classical world is the missing piece. The thing that explains gravitons, dark matter, dark energy, black holes, the beginning of time, maybe even the structure of the entire universe itself. And this is why scientists search for a theory of everything. Because right now, we're basically working with two different user manuals to operate the same machine, and neither manual knows that the other one exists. Imagine trying to fix a car with one book labeled Engine Rules and another book labeled Electrons Are Chaotic Little Gremlins Who Might Be Everywhere at Once. We want one book, one set of rules, one elegant framework that explains everything from galaxies to quarks. And the stakes get higher. If we ever truly unify quantum physics with gravity, we could finally understand what happens at the center of black holes, what really happened in the first trillionth of a second after the Big Bang, whether time itself is emergent, and even whether the universe is built on some deeper pattern, like a fractal. Which brings us back to James Hutchison and the modest theory. Before I play the interview, I want you to listen with an open mind. The modest theory isn't claiming to rewrite physics or replace existing models. It's proposing something new and intriguing. What if the universe is fundamentally fractal? Not metaphorically, but literally, from the smallest scales to the cosmic web. And even if that idea isn't the final answer, the path to a theory of everything often starts with exactly this kind of thinking. Simple patterns, unexpected connections, and the willingness to ask weird questions. And even if one unified theory of everything is never achieved, the search for it should eventually, at the very least, help us think of the worlds in the micro and the macro together. I've always said that if you set your sights high and fail, your failures will be better than most people's successes. If your goal is to be a doctor and you fail, maybe you end up being a nurse. If your goal is to be a physical therapist, you can't afford it, you drop out and join the army to finish your degree, maybe you'll be an IT guy and a science YouTuber like me. But if your ultimate goal is to be a manager at Little Caesars and you fail, you're going to live in a van down by the river with Matt Foley. That's a Saturday Night Live Chris Farley reference if you didn't get it. All right, so enough setup. Let's just get right into the interview. Everybody, enjoy.
What does that remind you of? Right? What comes in threes?
Almost everything.
Almost everything.
Pyramids. That little owl from the Tootsie Roll commercial.
Quarks. Quarks come in threes.
All right.
Okay.
Without further ado, welcome to the channel, James Hutchison. He's a computer scientist working on a unified theory of everything, which states that the universe is fractal. So I will just let him start by introducing his theory for a little bit, and then we'll talk and ask some questions.
Okay. Hello, my name is James. I've been working on something that I call the modest theory. That isn't its first name. The first name I gave it was the fractal universe, and then realized that that was already used quite a bit elsewhere, and I needed to differentiate myself. I went with the modest theory because basically this is a modest version of a theory of everything. And the idea behind it is that it's basically one sentence. And that one sentence is that the universe has a fractal pattern. That's it. Officially, that's all it is. And I did a lot of due diligence to be like, okay, if this is the fractal pattern, then what is this? What is that? And I realized that they're all rabbit holes. They all take extreme amounts of effort to really prove. And I didn't want to get sucked into that. I felt that being able to tell everyone, hey, the universe has a fractal pattern, knowing that information, what kind of conclusions can you draw just from that fact alone? And I wanted to get that out there as soon as possible and not burden myself with having to be perfectly correct. And so that's why it's modest. It's going to be wrong.
And then just for our viewers out there, what is your definition of a fractal pattern before we move forward?
So a fractal pattern is one that is something that is divisible, and it's a pattern in that it's a repeating set of rules that occurs across different divisibilities or different scales. And one example of this kind of fractal that I think the universe is like called a random tree. So if you go look at a picture of what a random tree looks like, you just see basically nodes, and the nodes have connections to other nodes. And if you look at the cosmic web, it looks a lot like a random tree. And you'll see this pop up in various different places. What are the rules of the fractal pattern?
Okay.
These are things that I've seen repeated. Maybe I didn't say this earlier, but I built a simulator. This is how I uncovered this information, and it was it's more of a true discovery. It's something that I came across by essentially accident. I was testing out a vibe coding platform. It wrote a bunch of stuff wrong. It didn't quite follow my instructions. So as I'm in the middle of fixing it, I go and I'm like, okay, you know what? I want to take a certain stance here and say that I was looking for basically to prove like is gravity just something like changing the field around it? And so I was trying to reproduce that. I didn't know what values in math to use, and I didn't want to take the time to like really go figure out exactly, because in the back of my mind I felt like that's why no one's finding this, because they're trying to solve it using the existing math. So I created a simulator with sliders on it, and using the sliders I was able to eventually reproduce what I was trying to. But in the process of creating like the range of values that those sliders could do, I found myself creating other things that looked very familiar. And
so essentially you're trying to create the universe in a slightly different way than we imagined it, but you're trying to get the same universe and the same types of patterns to emerge, and then bam, it'll be explained, right? That's the idea of the simulator, or at least to test it and hopefully get there one day.
Well, it was also like just modeling after things. Like, okay, so what do you see when you see like a comet, right? A comet has a tail. Like, what would that look like if the tail's pushing stuff out of the way, or the comet's pushing things out of the way as it moves through space-time? Like, what would that look like? And so that's kind of what I was modeling after. So talking about the fractal pattern, there's some definitions that do need to be covered. So first off, you have energy. What is energy? It's basically, I call it an aggregation or structure of energy, or lines and underlying set of fields. It's a recursive definition. So energy is just some sort of, you look at it and it's a movement, a propagation that happens. What is it really? I don't fully know for sure. Part of me in the back of my mind thinks it's just pressure balancing mechanisms, but it's a core part of it. And then the field applies to a given like aggregate structure. So like anything that like moves through space has the other stuff around it, and the other stuff around it is the field. And I think a great like metaphor for it is that you are the big meaty thing standing in water, and the waves pushing against you are the field. And when you get a really strong wave, it might shove you aside, or you try walking through it and you might wobble and stuff like that. So it's kind of that concept. But as you get to like, you know, different scales and looking at different things, the effects of that field become a lot stronger.
Okay.
Displacement means to just push it aside or deflect. It's a intentionally ambiguous term because I don't really know what displacement truly is.
Okay.
But it's sort of like, that's just,
you know, it's got to be
the end
there.
result. That's the end result.
Yeah. Okay.
Sometimes I use things called pressure and pressure gradients. And this is, you can think about like air pressure, but it could also be thought of as like the normalization rate or entropy rate, or chaos, underlying chaos of the stuff around you.
Okay.
We can go into that a little bit deeper later. And I talk about loops, which is just basically something that comes back to where it starts, and then of course the structure. So
okay.
So first off, the first thing here is that energy displaces the field. So you have energy, big energy and little energy, surrounded by little energy. Big energy pushes out the little energy. The little energy steers the big energy. It's kind of like a photographic mosaic. So, that looks like, there we go. It's better. So you kind of think about how like you have this little photo in here, and then you have a bigger photo that arises from the little photo.
Okay.
So that's kind of the idea about how the fractal pattern emerges.
So would these ideas kind of replace the idea of gravity, relativity, quantum physics, all of those things? None of them.
It's a different worldview. I think that's the main thing, is that like up to very recent time, you had everyone just kind of go through and say like, oh, this works this way, this works this way, this works this way, and they're all like disparate silos of knowledge.
You're trying to connect it together.
And this kind of connects it together and says they're all built on one common pattern or theme, and that common pattern is basically energy flow, which comes from these effects. Think of a push also as I steered you the other direction, right?
Mm-hmm.
So that's kind of where steering comes into play. And if you look at how Einstein described gravity, that's basically the terms he used. Steered. So next thing is you have something, so I called pressure is the normalization rate of the field. The underlying chaos. The idea there is that, like, let's say I ran my fingers through sand, you would see like lines, right?
Mm-hmm.
And something moving would be biased to move in the direction of those lines. As the wind shows up and whips it around, those lines fade.
Mm-hmm.
That's the normalization rate, essentially.
I saw the same thing when I was shoveling. I shoveled yesterday, and then you wake up and the wind blows it all around, and it's all going to kind of even out a little bit anyway. So.
Right.
Just wait till it's done. So
I created this picture. This is the idea about how like stuff comes into being. So like I think there's like the worldview that everything is just waves, and you get masses at certain values because they're standing waves. Mm-hmm. I actually disagree. That's what they are. You can see that like waves are something that happens later. So here's what you start with. You have a field, you have a shape, you get this pressure that then kind of sets this stuff up. You create paths, your paths create loops. Inside your loops, you get oscillations and spin, which gives harmonics. And then your paths and oscillations create waves. So waves are down here. Like you have to have this stuff first. So
and harmonics is audio sound.
No, harmonics is like, like a frequency. You got a frequency, you have things where it's like two things clash, but you get like these prime number things where, like just like in sound, you have like certain octaves or notes, and then you have like flat and sharp, right?
Right. So now that we've talked about the fractal pattern a little bit, what would you say that these filaments in the universe are?
So I think these are what I call energy tunnels. And right off the bat, a lot of people get hung up on the word tunnel. They think quantum tunneling. And I don't know if quantum tunneling is quite the same thing. But the way things seem to work is that you have like energy that goes and moves in one direction. It's pushing stuff out of the way. And that creates sort of almost a wall or barrier around it that creates resistance for anything else kind of moving into it. So stuff tends to funnel into these tunnels and then continue on for them. So that describes how a filament forms.
Okay. So I have two interesting questions for you. For somebody out there who's watching this video, if they're interested in, say, trying to help you test your theory or come up with some sort of math to explain it, do you think that could be possible? How do you think somebody would go about doing that? Do you think math will ever be able to explain your theory or no? Or do you think that abstraction kind of can't be explained by math, period? I guess that was like 5 questions, but
so that kind of leads into what I think the next step should be on everything, which is to build a better simulator. So maybe let's start by just showing the simulator in the first place, right?
Okay.
And I think right off the bat, you're going to see why the math is very difficult. So I got it paused right now, but this is something where it's like, is this real? Is this not? I don't know. This is me just filling with the knobs. But right off the bat, you can kind of say like, if I tried to make a math equation to describe this, it would be hell. especially with predicting the effects. Let me just try to tune things down so they're not so extreme here. Right. But, fundamentally, like if you look at the math at what other people come up with, their mathematical equations are like, here's the sum of something over like 4 dimensions, the integral of it. It's very difficult, but I do believe there's area in the math to reconcile it to reality. It's kind of like that's sort of the thing that you sort of learn here is that yes, there's stuff in here that resembles what we're used to seeing, but to get to those points requires like precise numbers. And so trying to basically fit what we've measured to be these precise numbers, I'm just gonna reset all. I think that's the big win, right? What I want to do at some point is get this simulator so that it can recreate a hydrogen atom from first principles. And I think being able to do that, like this stuff.
Yeah, start from square one with the most simple atom, which is hydrogen, and if you can create that, then you can start.
You can do that, yeah. Because
are you trying to be God, sir? No, I'm just kidding.
But I mean, like here, this is the loop of energy. This is essentially what mass is, right? And you can do a bunch of different things with this. You can change it to a vector field, which
yours would have essentially started making a planet.
Yeah. And it definitely like create, this stuff is very kind of wacky looking because it's all running at like relativistic speeds essentially, and we're not used to seeing that. I don't have this thing down to where it can effectively create like a solar system, especially with that tiny little grid and all that stuff.
So what would be the scale of this? This would be subatomic or atomic, kind of like particles, right? Energy particles.
It depends. I can load
what exactly does each dot represent? I guess let's start with that. That's an atom or a little particle of energy.
Yeah, it's sort of like a particle energy, but what I've sort of realized after making this is that I probably need like a function where it converts like what it's doing into more like a bound cloud of energy. I'm gonna switch things back off the vector because the vector field is definitely a more upper level, while normal field is probably more quantum. But yeah, I mean, like, yes, there's a little dot. The dot's the center of it.
What are those tiny, tiny little like white dots that are sort of spreading out? That's the field.
That's the field. Okay. Yeah. This is because there's no normalization. In real life, I think there's always normalization. So that's kind of one of those things where you talk about like, creating black holes and stuff like that. Like black holes definitely exist under certain circumstances. Okay, so this is actually, I'm going to pause this because this is interesting. You see the triangular shape that's formed here. What does that remind you of, right? What comes in threes?
Almost everything. Pyramids, that little owl from the Tootsie Roll commercial.
Quarks come in threes, but they're also unstable. So what I did some experimenting with this and found that the triangular shape is somewhat of a simulator artifact, because if you increase the number of computations per like these little square grids, you get triangles more frequently than you don't.
Okay.
So this looks a lot like a quark because you can see it's unstable. It rebuilds. That's what quarks do. They change flavors. So it's interesting. But that then leads you to believe like, okay, so why do we see quarks under these conditions? And the answer is like, it's a fringe condition. This is that barely hanging on. It's very difficult to get the messaging on this correct because there's a lot of things that.
Well, it's very abstract. Yeah.
It is abstract, yeah. And like another thing that's similar is that it's 2-dimensional, and so like there's certain things that I think only manifest under 3 dimensions that it can't show.
All right, so there you have it. Like I said, I think this is a very interesting approach. I had a lot of fun working with James. I like a hands-on approach to things. I think basically from talking to him, the idea that I got was just that we got something wrong between classical physics and quantum physics. If that's the case, maybe there's stuff that's wrong in the math. Let's just start over. And we have AI style vibe coding now, so let's use that to sort of try to build the universe from the ground up. And his theory is that everything starts with energy. So, that's why he built the simulator. He's definitely fine with criticism. He understands this is a insanely heavy undertaking, and that, like I said, one of the first things he said is that he doesn't want to be too burdened with getting everything right. He just wants to get the information out there in an attempt to, maybe work with other people, maybe just get the idea out there and flowing, and maybe get it into science so that there can be some scrutiny, or, like I said, people perhaps offering other ideas for him. So, I'm not going to do any simulations this week, but last week I did all simulations. That's all I did. So if you didn't see last week's live, make sure to go check that out. I crowded the solar system with a bunch of random planets twice until they all started, the first time until they all started crashing together, and the second time to actually try to make them stable. And then I did the same thing with crowding the Earth with a bunch of moons. So I put like 5, 6, 7, 8 moons around the Earth. So definitely go to make sure to check that out if you come here for the simulations. And if you've been following my 3i Atlas updates with all of my different live videos and sort of talking about NASA's press releases and some of the different amazing amateur images that we've been getting. Next Tuesday, like I said, I'm on every single Tuesday at 8 p.m. I'm live. So next Tuesday should be, I think it's 2 days before 3i Atlas closest approach to Earth. So we're definitely going to be doing a big comet update next week. We'll do 3i Atlas. We'll talk about the other Atlas comet that broke into 3 pieces. We'll talk about Lemon, because I know this will be, by next week, it'll be 3 weeks since I've talked about the comets. So we're going to get into that next week. I always try to get the video set up and get the thumbnail out there for you guys like a day early so that you can hit the subscribe button or the notify bell so that you can have it ready for you and that you know what I'm going to be talking about. And like I said, I hope you were able to listen to this today with an open mind, have a really fun time just exploring some super wild ideas and talking about quantum physics and things like that. That, to be completely honest, even plain old quantum physics as we know it, it makes no sense. Like I was just saying to Danny down in the comments, the first time that I really started to basically understand quantum physics a little bit, or get a little bit of a grasp on it, is when I understood that the entire thing about quantum physics is that it kind of doesn't make sense. And trying to reconcile that with classical physics has been just a thorn in the side of physics and science in general for a long time. And being able to at least reconcile them together, even if it doesn't mean one perfect unified theory of everything, would get us so far. So I said, I really appreciate everybody for tuning in today. I said, make sure to check out last week's simulation video. Make sure to be here next week for 3i Atlas, and I'll talk to you later. Bye.